Hello and welcome to today's lecture. Today we're going to talk about continue our discussions of graphs, and today we will be looking at one particular type of problems which is very common and very useful in many applications, and that is flow graphs. So here we have things like max flow. So basically, given that we have a graph representing say pipes, and then you can push, say, water through these pipes. And now the question is, in some sense, how much water can we push through these networks of pipes? So that's a typical max flow problem. And then there is a related problem called the min cut. And of course, that there is a strong relation between the maximum flow and the minimum cut, which is captured in this max flow min cut theorem. And then we also might be interested in not only finding a maximal flow, but actually finding the minimum cost maximum flow. And this will then cover labs 2.6, 2.7, and 2.8. And at the end, I will also mention about different network flow variants. So let's start with what is a network flow. So first of all, we have a network, which is a directed graph with a source vertex and a sink vertex. And each edge in this network has a capacity called the C of U and V. So that's the capacity on the edge between U and V. Sometimes it might be useful that if there is no edge between a pair of nodes, we can represent that with an edge of capacity 0. That's the same. And now we have a flow. We can assign a flow f of u and v to each edge in the network if it satisfies a number of properties. So first of all, the flow has to live up to the capacity constraint, so it cannot violate. It has to satisfy the capacity constraints so that the flow for each edge is less than or equal to the capacity of that edge. It's also the case that we cannot have negative flows, so all flows are positive or equal to 0. And there is also the conservation property, which means that the flow coming into a node is the same as the flow going out of a node. So basically it's the same, that the flow is the sum of for each vertex, the sum is 0, except for the source and the sink node. So of course the source node will have all the flow coming in, leaving it, and the sink node will have all the flow coming into it. But all the intermediary nodes should have equal flow in and equal flow out. And the flow value for this network for a particular source S is then defined as the sum of the flow from the source to each other node. So it might be multiple paths coming out from a source node, and then we sum up all those flows. So here we have some examples. So we have a network consisting of 4 nodes. So we have the source node to the far to the left, and we have the sink node T to the right, and we have 2 intermediary nodes, and we have 5 edges. So the number that you see on the edge is the current flow, and then after the slash, it's the capacity. So if we take the first image to the top left, we can see that from S to V, we can have a flow of 2, and then we can pass this flow on from V to T, because we're not allowed to have, so I mean the input flow and output flow has to be equal. So then we can push through 2 units from S to T. We can also see that we can push through 2 units from S to T through W. And now, so in the leftmost case, we have saturated the edge between V and T, so we cannot push anymore through that. In the second case, we have saturated the flow from S to W. And then actually there's one more flow that we can do, namely we can push one from S to V to W to T. So now all edges going out from the S is saturated, and all the edges going into the sink are also saturated. So clearly it's not possible to do any better than this, which means that we have here a maximum flow of 5. Um, in the bottom, we can see an alternative flow, which is called a blocking flow, because here we push 3 through S to V, and then push this 3 again down to W, and then from W to T. So we see that the edge between S and V and W and T are both saturated, so it's not possible to push any more through those. And here we cannot push anything from S to, well, we can push 2 from S to W, but then we cannot push that any further because the only outgoing edge is to T, and that's already saturated. And of course, since this flow is only 3 and we know that the maximum flow is 5, this is clearly a suboptimal flow, and we cannot do anything better. So if we reach this state, we are in what's called a blocking flow. So now the question is, how do we find the maximum flow for networks such as this? And here we will use a very elegant method designed by Ford and Fulkerson, which is called the Ford-Fulkerson's method. And it's a very simple iterative algorithm. And the core of the algorithm is send a flow F through path P whenever there exists an augmenting path P from S to T. And then, of course, we now need to define what an augmenting path is and how to find it. So in order to do this, we need the concept of a residual capacity. So the residual capacity of an arc is the difference between an arc's capacity and its flow. So here it's basically the difference between the capacity and the flow. And also what we do is that we introduce back edges, which allows us to reverse flows. So basically, if we made a bad choice, so in the previous example where I had this blocking flow, we made a bad choice. So if we represent the kind of possibility of reversing a flow, then we can do that using these back edges. So basically, the back edge is an edge in the opposite direction of the flow with the same same capacity as the flow in the other direction. So the capacity in one direction is the flow in the other direction. And now we can create a residual network. It's a network with back edges that have this kind of residual capacity, so the difference. And an augmenting path is a path from S to T in a residual network that we can add positive flow to. So if we take this particular example here, where we have so basically we have added a back edge from W to V, and now we can find a path here from S to W to V to T. So basically reversing this negative flow. So I mean, in the image we had before, we sent three units from S to V, and we sent 3 units from V to W, and we have 3 units from W to T. And this was then this blocking flow. So what we here can do is that we can push 2 from S to W, and then use this reverse edge or back edge from W to V, which is going in the opposite direction, where we can push 2 of the possible 3, because the flow is 3. And then we can push this 2 through V to T. So basically what this means is that we're kind of reversing the flow from W, or which is the same as we reduce the flow from V to W with 2. So instead of pushing 3, we only push 1. So that's this augmenting path. So this augmenting path is then this SWV T. And then there are a number of different ways of finding these augmenting paths. So in the original Ford-Fulkerson's method, these augmenting paths are found using depth-first search. And if we do it that way, then the time complexity becomes the maximum flow times the number of edges, which unfortunately is very slow on certain types of graphs. So for example, in this particular case, where we have this two outgoing edges from the source with capacity 100, and then there is a kind of link in between or flow in between with capacity 1. Then in the worst case, we might find a path SABT, and then in the next round we found a path SBAT, and so on and back forth. So in each iteration, the capacity of the flow is only 1. So it takes us 198 iterations to actually pass through all this 200 that we can pass through. So the max flow in this particular case is 200. So therefore, there is an alternative. It's called the Edmond-Karp algorithm. And here we replace the depth first search with a breadth first search. So the time complexity is now order VE squared. So it's significantly more expensive in terms of the number of edges. Now it's squared, and we also need the V. So if the flow is small, for example, then of course the Ford-Fulkerson is better. But in many cases, Edmond-Karp is to prefer. And the reason is, of course, that in this particular example, it will find the shortest path, which means that it will find the path FAT, or SBT for that matter. It will find one of them first, and then secondly, it will find the second one. So it means that it will only need 2 iterations to find the maximum flow in this particular case. So clearly, it's very useful. And here is just some code for doing that. I will not go through it. And here's the max flow code. So this is a typical example of code that's really, really good to have in your code library, because maximum flow algorithms are surprisingly useful in many different applications. So to summarize the maximum flow algorithms, we have the Ford-Fulkerson method using depth first search, which is then the maximum flow times number of edges. And we have the Edmond-Karp, which is basically Ford-Fulkerson with breadth first search, which is VE squared. And then there is a method called DDDD95, which is then much more efficient because it only goes to V squared E number of operations. Then there is a number of others like push relabel or preflow push, which is V cubed. And even a more efficient algorithms called binary blocking flow algorithms. Normally, for this course, usually Edmond-Karp is sufficient. If you want something a bit faster, one can recommend DDDD95. So DDDD95 algorithm is based on the idea that we reduce our max flow problem to the simple case where all edge capacities are either 1 or 0. So if that is the case, of course, we can just find the path through it. And the way we do it is that we scale down the problem by basically removing lower order bits. And then we solve this rounded problem. So we're basically looking at the 1-bit version of the problem. And then we scale the problem back up and added back the bits that we have rounded off, and of course fixing the issues that occurred due to that. So in the specific case of the maximum flow, the approach is that we start with all capacity in the graph at 0. We shift in the higher order bit for each capacity, so the highest order bit, which means that now the capacity is either 0 or 1. We solve this max flow problem, and then we get a solution to this. And then we add one more bit to the problem, and then we solve the problem again. And then now we have found the maximum flow. And then we need to go backwards, scale things back up, and then start with the maximum flow for scale down problem. We shift them up, doubling the capacities. If we then double all our other flows, then we have a maximum flow. And then we increment some of the capacities, and so in order to restore the lower order bits, and then we find the paths in the residual network to re-maximize the flow. So this is also relatively straightforward and simple method to implement. So it's slightly faster. So that was about maximum flow. We will now talk about the minimum cut. And the minimum cut is a very useful thing. And a cut is usually called an ST cut. So it's the cut between the partition of a network which is connected to S to the partition connected to T. So basically, it's a partitioning of the vertices V into two groups, CS and CT, such as the source belongs to CS and the sink T belongs to CT, and basically that there is only edges going from one of these sets to the other set. So basically we separate the sets and then there are a number of edges connecting these two sets. And then we can define the flow along the cut as the sum of the flow going from the sink side to the source side. So basically the flow going from S, so from any node in S to T. So that's the sum of that. So basically the sum of this. And then the capacity is basically the other way around. So basically that's the how much more flow you could send from S to T. So that's the general idea of the minimum or of the cut. And now the minimum cut is the cut with the minimum possible capacity. So in some sense, the optimal minimum cut is of course one where the capacity is 0, which means that all the flow is saturated. So it means that you cannot push anything more from the S side to the T side, from the source side to the sink side. So here we then have an example. So we have six node network, and here the minimum cut is the 3 edges here, the 3 red edges, which then has the 0 capacity. So to find the minimum cut, you compute the maximum flow, and then you find a set of vertices that are reachable from S. That is then in the residual graph, because we know that in the residual graph there is not possible. If there was possible to go from any of the other edges towards the T side, then of course we could push more flow through, and that's not the case. So therefore we can find these edges. So basically this, you can call it the bottleneck because it basically prevents us from adding more positive flow to this. So then we have the max flow min cut theorem, which states that the maximum flow is equal to the minimum capacity over all ST cuts. So it means that we know that the minimum capacity of the best ST cut is the same as the max flow. So therefore there is a very close connection. And then finally, we will be talking about minimum cost maximum flow. So as I said, we can then find of all the possible maximum flows, we are now interested in finding the maximum flow with the minimum cost. So what we do is that we extend the definition of a network flow with a cost per unit of flow on that edge. So basically, how much does it cost to push 1 unit of flow over this edge? That is the cost, here called K. And then the cost of a flow is, of course, the sum you multiply the cost with the flow, and then you sum up that for every edge. And then, of course, the minimum cost maximum flow of a network is the maximum flow with the smallest possible such cost. So very straightforward. So one important observation here is that now the edges in the residual graph must have also their cost determined carefully. So that we might have an edge VW with a capacity CVW, and the cost per unit flow is of course K. And if we let FVW be the flow of that edge, then the residual graph has 2 edges corresponding to this. The first edge, BW, is the capacity that we can have with the cost K, and the second edge has a negative cost. So the edge, basically the back edge, will have a negative cost because we're reducing the flow. So therefore, we're also reducing the cost. So you need to keep this in mind. Yeah, it's clear that the minimum cost maximum flow generalizes maximum flow, since we can just set a unit cost to the for every edge, and then it's exactly the same as maximum flow. Which of course means that if you implement a minimum cost maximum flow algorithm that's efficient enough, you will also solve the maximum flow problem. It also generalizes the shortest path because basically we set the cost equal to the same, and then we have some maximum capacity, so the capacity doesn't really count, and then it's the same. And in order to compute the maximum flow with minimum cost, we can adapt Edmond-Karp. So instead of using breadth first search, we can now use Dijkstra's shortest path algorithm to find the shortest path, but of course in the cost part. So basically the minimum cost augmenting path, and then we can use this and kind of select the augmenting paths in increasing order of cost. Then finally, there are some important variations, basically how to rewrite your graphs such that we can apply maximum flow to them. So one thing is that it might be multiple sources or multiple sinks. The way we do there is then we just add a super source or a super sink with infinite capacity edges to all the sources or all the sinks. So basically just adding one more node, and then we have a unique source and a unique sink. It might also be the case that we have vertex capacities. So instead of having capacity on the edges, we have capacities on the vertices. In this case, we have to split each vertex into two, and then add a bidirectional edge in between them with the vertex capacity. And then, of course, we need to, all the ingoing edges has to go to the first, kind of if we split it up from left and right, we have ingoing to the left and all the outgoing from the right. So we need to rewrite our graph, but then that can be done. So in summary, I've been talking about network flow problems. I talked about residual graphs where we add back edges so we can reverse the flow. And when we have these residual graphs, we can then define augmenting paths, which are paths from the source to the sink, which improves the overall flow in these flow networks. I've talked about or described three different algorithms for solving the max flow problem, namely the Ford-Fulkerson depth first search version, the Edmond-Karp breadth first search version, and then Dinnick's algorithm for max flow. We also talked about min-cut, which is basically the dual to the max flow. So given that we found the max flow, we can also identify the minimum cut. And this is then captured by the max flow min-cut theorem. And then we talked about extending the maximum flow to the minimum cost maximum flow, which we could do by replacing the breadth first search part of Edmond-Karp with the Dijkstra, and to do this search in the cost graph, and they're taking the cheapest augmenting path. And finally, also talked about how can we deal with having multiple sources or multiple sinks by adding a super source or a super sink, or how to deal with vertex capacities by splitting up each vertex in two and adding a dual bidirectional edge with the capacity of the vertex in between them, and rewriting the graph so that all the input edges come to the one of those two nodes and the output edges all goes out of the other. So that's all for today, and I should be clear about that This is a very important algorithm, this max flow, and it will be very useful in many applications. So I strongly recommend that you spend some time learning about it and doing good implementations of it, because you will have a lot of usages for it. Thank you very much and good luck.